Yeah, hi. In this video, we're going to do a testing hypothesis for the population mean, which is mu. So our parameter of interest is mu. We have a single population, large sample, and we want to find out how do we test the mean, whether mu is equal a certain value or not. So what is that value? It's going to be mu sub 0 that we want to compare with. So to do that, we need to collect data, and this is a data summary. So we have all these observations. We keep track of the sample size, the sample mean, the sample standard deviation. We need to know the value we're going to compare with. I call it the target value. And we need to think of alpha. What is our significance level or probability of type 1 error, or our tolerance for error in this case. We cannot have zero tolerance for error. It has to be some value, and typically we pick 5% as the default value. So here is how we formulate a statistical test for this problem. We pick our null hypothesis will be mu equal mu 0, because this is the one that's not this. And our alternative is, we have three possible problems we can formulate. One is mu is larger than mu 0. So I'm interested in finding out whether mu is larger than something, or mu is less than something, or mu not equal to something. So in any one of these cases, my test statistic, my data summary from here would be x bar minus the mean of x bar under, remember we said the hypothesis test is we try to prove this is true by showing this cannot be true. So the way we do that is say, suppose this is true, and then we're going to reach a contradiction that say that can't happen. So under that assumption, the mean of x bar would be mu 0, and when I divide by the standard deviation over square root of n, because most of the time sigma is not known, so I replace it by s, its estimate, and that should be fine. And then I have a rejection. I'm going to deal with my rejection region. So I'm going to create a rejection region. If this is my test, first one, my rejection region would be reject H0 if z is larger than z alpha. And that's the critical value I want to compute. And we know how to get those. We did them in the previous chapter. And if this is my test, so this, we call this an upper tail test because it's larger than. If it's less than mu 0, we call it a lower tail test, since I'm going to be working with the lower tail of the normal distribution. And in this case, we reject H0 if z is less than negative z alpha. And if it's mu not equal to mu 0, this is called a two-tail test. And in this case, I take, instead of z alpha, I take z alpha over 2 and split it into two parts. So this makes it larger than this, and this will be smaller than this value. And I reject if I'm above the larger value or less than the smaller value. Okay? And then the decision, if the observed value is this, or the statistics, the test statistic value called also the observed value is in the rejection region, we reject H0. If not, we say don't reject H0. And then the conclusion would be at 5% significance level, there is either sufficient statistical evidence to favor HA if we reject, or insufficient if we do not reject. Okay, because the assumptions for this would be we need a large sample and more than 30, and the sample is random. Let me show you the graph for this test so we can have a sense of. I'm going to show you a graph for each one of these. So if it's an upper tail, lower tail, or a two-tail test. So if I go to my tablet, I already graphed those for you. So I have this situation here, and this is my z alpha. So this is my upper tail, and then this is my rejection region. This is my non-rejection region. I don't call it acceptance region because it's proof by contradiction. And if my z, the test statistic value, is up here in the rejection region, I reject. If it's not, I don't reject. For the lower tails test. So this is the case where my alternative A is mu is greater than mu0. For this case is this is my alternative, mu is less than mu0, and C is the alternative that I pay attention to. So that's a lower tail test, so I'll be working in the lower part of the graph. My critical value is negative Z alpha, and if my test statistic value I computed from the data is below here, I reject. If it's up there, I do not reject the hypothesis. Same thing here. This is the situation where mu is not equal to mu0, and not equal means either larger or smaller. So I take my alpha and split it into two, and you can see this Z alpha is going to be larger than this here, and this negative Z alpha over 2 is smaller than this one here. And so I compute my Z, and if it's up there or down here, I reject H0. If it's not, I do not reject H0. Okay, so that's my graphically what's going on. So let's do an example on this. And here is an example. So I want to test the hypothesis that a weight loss in a new diet program exceeds 20 pounds during the first month. So here is a problem. Maybe you're designing a new pill or a new diet program, and you claim before you sell it that it exceeds 20 pounds, and you need to prove that before you can sell it and market it that way. So you collect a sample of basically 36, which means you test that product on 36 patients, and that's X bar. You find out the sample mean is 21 pounds, a little bit more than 21. But what you want to know is whether in the population, if this product is used for thousands of people, hundreds of thousands, would that exceed 20? So it seems to exceed 20 for 20, for 36 people on average, but would it exceed it for larger, for the whole population? So in that case, we need other pieces of information. We need the sample variance turned out to be 25 here. So the value you're going to compare with is 20, and we're going to pick alpha 5%, the default value. So here's what we are interested in, is whether mu is larger than 20 versus mu not larger than. The way we read this, not equal 20, but not larger than 20. It just, we write it that way for convenience, but what really means is that mu is anything that's not the alternative. Okay. So we do our test. So now we're going to summarize our data, and here we get Z equal, that's the formula, X bar minus mu0 over S over square root of N. So X bar is 21. That's the data summary we had. And we're going to subtract mu0, which is 20, divide by the standard deviation. Or we were given the sample variance, or we wanted the sample standard deviation, so we take 5 instead of 25. Be careful when you are given to use the information you want, not what's given sometimes. And then divide by the square root of 36. Simplify this, and we got 1.2. So what's the critical value we're going to compare with? This is a one-tail test. Alpha is 0.05, so I'm looking for Z alpha, or Z 0.05, and from this Z table, or from that 4 or 5 numbers we already talked about before, we know that Z 0.05 is going to be 1.645. Okay, so that means my rejection region would be reject H0 if Z is larger than 1.645, and graphically that would be I would be picking this graph here, where this value is the 1.645. My Z is 1.2, so it's not going to be above, it's going to be down here. So I do not reject H0. So my decision is do not reject H0. So although my X bar, the average loss for the 36 in the sample is 21 above 20, I cannot say with great deal of confidence that I really my product will the overall the population targeted population will exceed 20 pounds in terms of weight loss. So my decision do not reject H0. So what does that mean, do not reject H0? So that's why I need this conclusion, because my conclusion is based on a 5% significance level. So that's how I got my alpha 1.645. So I need to state that. So at 5% significance level, there is, did I have enough evidence or not? My evidence was insufficient because I did not reject. If I rejected, I would say sufficient. So in this case, I had insufficient statistical evidence to conclude that the weight loss will exceed 20 pounds. Okay. So as an exercise, how would you change your claim if the weight loss is 19.5 pounds? So I want you to try that. And let's see what would happen if we had a small sample. So if our sample wasn't large, what would happen if we have, so this is a small sample inference about the population mean. Everything is going to be the same for a small sample, except that instead of z, we're going to be dealing with a t. Okay? So the parameter is mu, sample data and x bar as target value, point estimator is x bar, its mean is mu, the standard error is s over square root of n. Same structure here, mu equal mu 0. The alternative mu larger than upper tail, lower tail, two-tail test. Now the critical value is not going to be t. It's not going to be z, is going to be t. It's going to be t alpha if I'm dealing with an upper tail test, negative t alpha if it's a lower tail test, or t alpha over 2 if it's a two-tail test. But also I need to keep track of the degrees of freedom to find out the actual value, which is the sample size minus 1. Okay. So in this case, my test statistic would be x bar minus mu 0 over s over square root of n, same as before, except I replace sigma by s and z by t here. And same structure, reject for the upper tail, we reject if t is larger than t alpha. For the lower tail test, we reject if t is less than negative t alpha. And for the two tail, we reject if t is larger than t alpha over 2 or less than t alpha over 2. And the graphs, we're going to have 3 graphs, one for each, which are quite similar to these ones. And so let me show you. So for the upper, the only difference here is going to be, I would have t alpha with the degrees of freedom, negative t alpha here, and this would be negative t alpha over 2, and this would be t alpha over 2. Okay, and the same structure because I have smaller samples, and those t alphas are going to be, this t alpha is going to be probably larger there because that would be the penalty I have for having a small sample. So I go back here. So if my t statistic here, the statistic value is in the rejection region, I reject H0. If it's not, I do not reject H0. Okay, and then same conclusion, either sufficient statistical evidence or not, based on the significance level I have to favor the alternative. And you don't try to favor the alternative, you spell it out. So the assumptions for this is I have small sample, less than 30. The sample is random. I have normal population, and my variance is not known. Okay, so I use S instead. Let's apply it for this problem. So for the sample data given below, this data here, n is 25, x bar 21.3, s squared 25, and mu 0 20, f 0.05. Test the hypothesis that the weight loss in a new diet program exceeds 20 pounds. So it's a similar problem, but based on a sample of 25, but now my x bar is 21.3. Okay. So again, mu equal, so my critical value in this case would be t.05. My degrees of freedom are going to be 25 minus 1. And if we go to the t table, remember the t table, and we go to 0.05 and the up in the numerator, and then we go to 24 degrees of freedom and pick that value. Is going to be 1.711. So let me show you that here. So that this would be, if I go here, this would be my t table. If I give you a structure here, and I want the t 0.05 because it's a one tail test, and then I want the 24 degrees of freedom here. I go these two lines, and that would be the value I'm looking for, which is 1.711. Okay, so now this is my mu 0. This is my this is my null hypothesis. My alternative is I want to test whether mu is larger than 20. So my test statistic, it doesn't matter whether it's a one tail or a two tail, it's the same. What matters, what changes when the alternative changes, is the critical value here. So I have the formula, I substitute, so it's x bar is 21.3, mu 0 is 20, s is square root of the variance, it's 5, n is 25, so that's the square root of 25, and it's 1.3. So my rule says reject h0 if t is larger than 1.711, but it's not, so I do not reject. I have the same situation as before, and then I conclude at 5% significance level there is insufficient statistical evidence to conclude that the weight loss in the new diet program exceeds 20 pounds for the first month. Now I want you to do this. Test the claim is not equal to 19.5. What would happen if it's not equal? All right, thank you.